Barcelona. And he will talk about amplitudes for EFT. Please. It's for 2 hours.
Okay. Okay, thank you very much. It's nice to be here. I hope you're having fun there. Okay. The intention of my lectures is a little bit to combine probably two kind of fields you are listening here. One is about amplitudes, and the other is about effective field theories. Okay, in the case of effective field theories, you've been mostly has been mostly devoted from the idea of expanding a Lagrangian, okay, in fields. Okay, so the idea is to kind of repeating the same thing, but doing it all the time from amplitudes. Okay, not going to fields to derive your effective field theory. Okay, so I'll be talking about a couple of things. Okay, so the first thing, as I was saying, is to get into the idea of effective theory. Okay, in this case, we will talk about amplitude. So the F of effective field theory, the F will disappear. We'll talk about effective theories. Okay, and this is again, as you heard about amplitude, this is a shortcut. Okay, we go directly to physics instead of going through the process of building your fields, building your Lagrangian, building your Feynman rules. Okay, it takes a lot of time. Okay, to get down to physics. Okay. And this will be the first step, okay, to see how you, in the same way that you were doing effective field theories, you can do here some kind of effective theories from amplitudes, okay? That will be the first part. The second part, I'll try to go beyond tree level, okay? And as you will know, as you know, and I will explain it later, it's very important, renormalization in effective field theory, okay? So I'll do it using on-shell methods, okay? That means that loops, instead of calculating them from the Feynman diagrams, will be calculated from always on-shell quantities, okay, tree-level quantities, okay. And my point here is to show, okay, that this is, let me see if you can see here, yes, this is simple, it's elegant, it's efficient, and most importantly, you get so many selection rules that tells you there are many zeros, okay, that from Feynman you don't see them, okay. Not only that, also you will see some clean relations in between when you calculate loops, okay, that when you calculate, sorry, one loop correction from the level amplitude that you don't see it from Feynman approach, okay, and they also the main thing of amplitudes, okay, everything is useful, nothing is a wasted calculation, you always recycle, okay, you calculate the level amplitudes from the level one loop when you have one loop, and goes on. So, okay, the process is always built up in previous calculations. Okay. So, any questions at any time, you can stop me. I don't know how you proceed here, if, but it's to me okay if you stop me anytime. Okay. So again, even that I will call EFT. The idea here, okay, the F has come from effective now, not from fields. Is the idea is the same idea that you have been using to as derived here by the lecturers, previous lectures about effective field theories. Here we will not use fields, but the same idea of effective to build a effective theory at low energies will be done here the same, but from on-shell amplitudes. Okay, so again, I will determine this thing from amplitudes where now the states have are defined by their momentum and their helicity. This is the most important thing, okay? And I have some convention here that I'll tell you later probably which one, probably are different from others. But at the end, for example, my amplitudes are from incoming particles, and there are other ones that I'll tell you because I'll be using also the spinor helicity formalism, okay? But are here, so there's subtleties with signs that are nasty, but okay, I will tell you before. Okay, so you already heard, let me put it in the background of what you heard already of effective field theories. Okay, effective field theory is a kind of only an expansion. You have your Lagrangian, you don't know what it is, your theory, but you define that there is some physics scale lambda, okay, that is very heavy, and now you expand. You use a tailored expansion of derivatives, fields, okay, over this lambda. Okay, and now you have an expansion in orders of lambda 0, lambda square. Okay, and this is an expansion you do. Okay, and of course you know this theory, and kind of spirit is the same as harmonic oscillator or Hooke's law in classical mechanics. Okay, you know it works. Hooke's law works very well for small distances. Okay, for a small displacement of the oscillation. Here, you know it works very well for low energies. Should work for low energies. And it's universal theory. It's not a complete theory, but it's universal because everybody has to follow these things. Okay, and this is the idea of building up the standard model that is the leading term in this expansion in lambda. Okay, and the others are corrections suppressed by 1 over lambda 2, 1 over lambda. I didn't put here the dimension 5 operators, lambda 6, whatsoever. Okay, and now of course yes, forgetting here because I'm assuming. If you assume lepton and baryon number, of course, next order is dimension 6 operators. Okay, in the case of the standard model, you already heard there are many of them. Okay, here is the table, but you already, okay, you don't have to look at it. Okay, you already had lectures on this. Okay, and only tell you that it's not easy to get this thing. Okay, because there's a lot of redundancies. Okay, remember the fields are not physical quantities, so you can redefine it. They're like coordinates. You can change coordinates. Your physics doesn't change. Okay, so fields you can change, reorder your fields. Physics doesn't change. Okay, so it means there can be a lot of redundancy. You have to do the exercise to be sure to get the important ones, and they're not. And to be sure that you cannot eliminate some of them. In fact, many people, previous papers miss this thing. Okay, so it's not something easy. Okay, you have to spend time to get this list of operators. Of course, you can do it. Okay, but then it takes time. So the idea here is not start from these operators. Okay, that built up your for example here dimension 4 standard model, dimension 6. This operator I was showing to you that, as I was saying, contains many things off shell. Okay, but to start with something that is on shell. Okay. So, and the crucial point, of course, the p-squares of the states are 0. In the case I'm starting here with always massless states. I'll talk a little bit at the end about massive states, but right now here everything will be about massless states. In fact, the couplings in the standard model are defined for massless states, so there's no problem here. After that, the Higgs get a BEV, and now you can start talking about massive states. But at the level that the Higgs does not get a BEV, you define the interactions. You can define it with for massless states. Okay, and the key point, as I was saying, is that they have definite helicities, plus minus. Okay, for massless states. Okay, so there's an important gain in simplicity. Okay, dealing with physical state. Okay, so for example, a gauge boson, A mu has 4 components in it, and this is what you have made you suffer. Okay, when you calculate things, because you have 4 components that you have all which contract with another. You know, at the end there are redundancies. Okay, that is the gauge invariance. Is what it's doing is eliminating your redundancies. Here you start with the physical state. There is nothing about gauge redundancies. Okay, that says this is the simplicity that you start with. Okay, so I was saying before. Okay, I'll go through I'll use the spin-helicity formalism that you already heard about it. Okay, I'm only putting here just to recall that I'll be talking about this angle spinors, square spinors that should be contracted among themselves. Okay, and here I have many conventions. Okay, it's only a question well, I mean, sometimes there is subtleties when you go from minus p to p. In my case, I put an I here. Okay, so it's just some convention here doesn't matter. At the end of the result, you can follow with any convention. Okay, so to be sure that if you see something will be in these conventions. Okay, now, so let me do it for the standard model. Okay, thinking the standard model. Okay, we will not do the full standard model here, but the idea is, for example, is to consider standard model as an effective field. You consider as an effective field theory. Here we consider as effective theory of amplitudes. And now the same idea as we were having of expansion in fields. Okay, we now have an expansion in some sense in these angles brackets or square brackets over lambda. Okay, so it's the same idea. Okay, but instead of expanding field here, you have already these brackets, okay, that correspond to momenta, okay, so it's a kind of a low energy expansion, okay. And now, of course, of the order lambda 0, okay, where lambda does not appear, this is what we call the standard model. Okay, now we have, I mean, as we can build a theory. Okay, now what we need from the standard model, we only need the fields. Okay, so for example, we tell us that there is a vector and two fermions. We know, as you heard up already, that's the only way to build up a 3-point amplitude. Okay, with this bracket, that's the only one way. Okay, if you, for example, in the case I'm taking elicity minus, you take a plus, and now this will be all squares here. Okay. Now the other thing we have to know, of course, is also the global symmetries. Okay, to build up this amplitude. Okay, this is the kinematic part. It's fixed by, let's say, by the elicity of the state. This is minus. Okay, for when I put psi will be minus. This is psi bar will be plus. So a fermion with minus elicity plus, and a vector with minus will be this case. But if there is some symmetry, you have to put some invariant tensor here. For example, if this is some non-abelian group, okay, so I have to put things and a coupling in front of it, okay, that is the gauge coupling. And the same I have to do with, okay, if I have a Higgs, okay, to two fermions, okay, the only one I can write is this one, okay. And the important point is that I have to do all the ones I can do it, but this is limited. The elicities are not limited. For example, this is minus, this is minus, and this is plus. I cannot have minus, minus, minus. Okay, that's very important thing. Okay, in the standard model at 3 level, okay, without using lambda, so lambda is 0. There is no lambda here appearing at this order in expansion in lambda. The vertices have definite elicity. I cannot choose all the elicities. Okay, this is minus, minus, plus, and here is minus, minus. Okay, so I cannot have Higgs and minus plus. Okay, this is fixed because I can only build this one. Okay, so you have to spend time to see that this is the only one you can build. And if I go for 3 back gauge bosons, okay, you realize this is, you already went through the probably using lectures, that this is the only one you can build, and it contains minus, minus, a plus. Okay, I cannot build something with minus, 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 or plus, plus, plus. Okay, so this order, I mean, the elicities are kind of fixed. Okay, and yes.
Before you proceed, could you explain? I mean, so I think some audience are not familiar with this. So could you just explain what the mass dimension of the couplings of these 4 vortices?
The dimensions of the coupling?
Yeah, mass dimension of these couplings. Yeah.
Decoupling, this coupling? This is an amplitude. Okay,
mass dimension of the amplitude. Yeah, sorry. Yeah.
Okay, yeah. Thanks. Yeah, it's important to know. Yes, because this is based on dimensional analysis. It's important to remember that the dimension of an amplitude, 3-point amplitude, is 1. 4-point amplitude is 0. Okay, so you have something like an amplitude of n-point amplitudes with n particles. Yes, go with so an amplitude here. Sorry. So an amplitude of n states will go like m to the n minus 4, no? Sorry, 4 minus n, no? Four minus n. Okay, so n is 3-point functions here. We are looking at a 3 pt. Okay, so this is dimension 1. Okay, when we go to 5, it will be 1 over dimension. This is important. Yes, I didn't. Okay, I'll leave it here. This is important because now you have to build something has dimension 1 and indeed has dimension 1. Okay, this is. I was fast here because I understood this. You had lectures, so this has dimension 2 because this brackets has dimension 1. Each one, the square or the angle, both has dimension 1. Okay, so this is dimension 2 divided by dimension 1. This is dimension 1 thing. This is dimension 1 thing. All of them has dimension 1. Except that this is 4 pt. Here n is 4, so 4 minus 4 0 is dimensionless. Okay. Okay, and now yes, and now the couplings are dimensionless. Okay, the couplings are dimensionless and priori are coefficients, and the idea is that these are your building blocks. Okay, this is how you define your theory. Okay, this is the minimal set of amplitude that you can build. with the lowest speed particles, and now from that you built in a more complicated amplitude by matching these things. Okay, that I understood that you had already lectures on this. Okay, but I'll briefly come to this point also. Okay, so in some sense this is the only coupling you can have in the standard model. Okay, but as I saying, okay, these are 3 PTs, and the only 4 PTs you are allowed is the with a dimension less coupling is with 4 Higgs. This is for 4 Higgs here. Okay. It's nice you spend some time to get this, because you will see how easy, some sense, you get the standard model. Okay, you have to spend time to realize that this is the only thing. That, as I said, the important point coming out of here is some elicities. You can have some elicities here, and some of them you cannot have them. Okay, so that's probably one of the important message. But everything is a kind of easy because you spend time and realize, I don't know, in 10 minutes that there is nothing else you can do. Okay, so the idea of, let me remark here, the idea of a gauge invariant is not here, okay, because we didn't start. The idea of gauge invariant is in your fields, because you start with these redundant fields, A mu, or H mu for the graviton, contains 2 degrees of freedom that you don't want to study. You want to study only the plus and minus helicity, and now you have to eliminate them, and this is the gauge trick. Okay, the gauge trick is a trick to get rid of all these extra guys. You don't have here the extra guys, so there's nothing about the gauge. Okay. And now, as I was saying, I hope it was explained to you. Now, from these 3 PTs and 4 PTs, you can build any higher standard model amplitude. Okay. And the amplitude have to have these properties that it has to have singularities are only coming from single poles, so interchange of particles. Okay. For example, here in the T channel. And the idea is when you go on shelling these particles, okay, any amplitude, higher point amplitude must factorize into smaller amplitudes, okay? And I guess you heard about it. I had an example here. Let me see, I can go to it, okay. Had an example. Okay, I don't know if you see it, because we will use this amplitude. I'll go slowly, and I'll use this amplitude later on to calculate. Remember, to calculate loops, you need 3 levels. So first you calculate 3 level, and after that you go to loop. Let me close here, it's noisy. Okay, and the amplitude you can see as an example of what I was saying is this amplitude here. Oops. Yes, this amplitude here. This is standard model amplitude I want to calculate with 2 fermions of helicity minus, vector boson helicity plus, and a Higgs. Okay, we'll need this amplitude later. And now it takes you a little time to see that the only thing you can build up to have these helicities, okay, plus minus minus is this one. Okay, remember that if it's minus, I have to have brackets. I have to have, for example, the 1, 2 angle brackets. Okay. And I have to have this 3 plus, I have to have angle brackets. If it's angle brackets, I have to put it down here. Okay, so I have 2 3s here that fulfill the necessity to describe this particle of spin helicity plus, but spin 1. Okay, I need 2 of them. Okay, and the rest, okay, when I fix these 2 and these 2, the rest, okay, let me probably mark it. Okay, so this is fixed by helicities. Now the rest you have to fill. Okay, with the other fields, here you can put 4 and 4. Okay, 4 and 4, and 2 and 2 has to be the same in order not to change the helicity of the full diagram. Okay, so I cannot put a 2 here that I don't put down. But of course, could be a 4 here or could be another. It can be also a 1. Okay, so I have few little possibilities to build up this thing. Okay, and this has to do with the fact that this amplitude, you have to specify who is charged under the standard model. Okay, so this is a gauge boson here, W. Okay, but in this amplitude, I'm not sure if this that is a triplet, let's say, of SU2. Okay, so I have a global symmetry here, SU2. So you'd have to tell me who is also. There must be another, to be invariant. There must be another state charge here. One of these things has to be charged. Of course, if you don't tell me, I cannot completely know that here's a 4 to here. Now, if you say that it's a Higgs that is charged, now there can be a channel here that could be the interchange a Higgs, okay, a charge Higgs, okay, because the Higgs is charged, it can go to this one. Okay, so inside this diagram, we know there will be a Higgs in this S channel, okay, because I declare it charged, and now I have to have a pole in the 3, 4 here. Okay, so I have to put a 4 here, I have to put a 4, and now again I have to tell you who is charged under the symmetry, the 1 or the 2. In this case, I took 2. Okay. So the key point is once you fix the helicity, you already almost have everything, except that you have to tell me of also the fields who are charged. Of course, in the standard model, we know the Higgs is charged and the rest U2. And here, one of the two fermions, there must be a doublet, fermion a doublet and a singlet, okay? And in this case, I put here the 2, it means that the 2 is the doublet, okay? Why? Because now this amplitude, when I look at it, okay? Let me, oops. I cannot take it, okay, now, okay. When I look at this amplitude, let me go back to here, okay? When I look at the amplitude, as I said, I know now that there is when 3, 4 goes to 0, there is a pole, okay? And when 3, 2 goes to 0, it has a pole. And 3, 2 and 3, 4, you already know is related with the P3, 4, P3 plus P4 square. And 3, 2 is related with the P3 plus P2 square, okay? Hope you did this before, okay? And by the way, I know this amplitude except the constant, okay? So how do you determine the constant is because, as I said, now I have a pole when the 3, 4 goes to 0, okay? Related with the P3, 4 going to 0. P3, 4 square going to 0 is equivalent to taking 3, 4 angle bracket going to 0. Okay, and now I know I have the required factorization. Okay, so it means that when the 3, 4 there is a pole, I mean there is a particle. Okay, is the Higgs particle, because you see this is the pole here in between the 3 and the 4. Okay, so I know I have in my theory already showed you before. I know that they have this vertex, a vector coupling to the Higgs, and a Higgs going to fermions. Okay, so now on the pole I see that this should factorize into this guy, okay, and this is what I'm writing here. I'm writing this guy is this guy, okay, this amplitude is this amplitude, there is 1 over P squared coming from here, and now there is this vertex that is this one here, okay? And now the couplings are fixed because I defined it before, okay? I defined that this goes like with a coupling that is what called Yukawa coupling, and I defined this to go like G, like this, okay? So everything is here fixed when I go on shell on one of these particles because it's based, now I can relate with my previous 3PT that were the definitions of my couplings, okay? The previous one were definition of my couplings, okay? And now with a little bit of algebra I show here, okay, multiply by this, and now probably I should skip it here, but with a little bit of algebra, okay, I can rewrite this thing exactly as this quantity like here, okay? A little bit of algebra to remember that, I mean, the trick of multiplying this up and down, and now using the fact that this is by definition in the spin organicity, the P3 plus P4, you put P3 plus P4, but 3 contracted with the 3 is going to be 0, so it only remains the 4 here, and I go on. Okay, here it is an example, you can do it. It's a very simple exercise, which of course I'll get that this is exactly what I started with, okay? But now I fix the C is exactly what remains, okay? So in this way, by going on shell, I fix the constant, okay? And I fix all the amplitude in some sense in a quite simple way, okay? You only have to be a little bit ordered, not to leave any factor, but now I can know the factor here in this way. And if you want to check, also you can go to the other pole. Here, when this goes to 0, there is a pole, okay? And you have to see that there is another factorization and see that everything match, okay? You can keep one is to define your C, and the other is to check that you did the right thing, okay? Okay, okay. So this is the amplitude. Okay, so calculating the amplitudes it can be easily calculated in this way. Okay, in the standard model. Okay, and of course you can do it also a la Feynman and get the result in spin analyticity, or there is other techniques that probably was taught to you. Okay, by doing the shifts in the Z plane. I don't know in the momentum shifts in the momentum. I don't know if you went through this thing, but but there are other ways to do it. Okay, I'm saying in most of the cases on the standard model is very simple. It's only just consistency of the theory and factorization. Consistency, your amplitude has to follow helicity rules, okay, because involving some particles, okay, and factorization, okay. And now you define every 4PT as a function of these guys. And these are the guys, these are what I call building blocks. Everything should be reduced to these ones. And these are here where my couplings appears, okay? Okay, so this will correspond to the standard model, okay? But we want to do beyond the standard model, okay? So in the same way that in field theory, you were expanding in fields and moment and derivatives over this lambda associated to the scale of new physics. Here we are thinking to do the same. Okay, so now we can go to order 1 over lambda. Okay, so this will correspond. Lambda is the scale. I can associate the scale to new physics beyond the standard model. So there will be amplitude suppressed by this lambda. Lambda is big with respect to, let's say, today's experiment. Okay, so TeV, so lambda can be above, a little bit above TeV. Okay, and now you have an expansion in the standard model. And now you have, of course, if you use this lambda in your amplitudes, you can have more amplitudes. Okay, you can have more. Yes, the similar we build here. These building blocks. I can increase the number of building blocks. Okay, there's new building blocks at order 1 over lambda. There is only one extra I can write. Is this one? Okay, that involves 2 Higgs and 2 fermions. Okay, and this is associated with the dimension 5 operator in the standard model. Sorry not to put you here. It should be now in the standard model. I should tell you how they transform. So it's important not only the kinematics here, but also how the fields transform under the global symmetries. Okay, so if the standard model, I should tell you, yes, I have to put here some extra epsilons that contract. For example, these are 2 doublets. These are 2 doublets. So I have to contract not among themselves because it will be 0. Contracting 2 doublets among them if it's only the same guy is 0, but I have contracted the doublets like this and this. Okay, so there will come 2 epsilons here. Okay, that I'm sorry not to put I'm not going to, otherwise will complicate more. But there's the exercise you have to do. Okay, so this I'm only talking about the kinematics. Okay, but there will be some invariant tensor here related with the global symmetries of your theory. Okay, in general, this is valid for any theory. Okay. And this is, you can see that order 1 over lambda, that's the only one you can write. There's nothing else. Okay, remember that this is our 4 fields now, and an amplitude with 4 fields. Sorry, with 4 states. An amplitude with 4 states is dimensionless. Okay, so this is dimension 1 here. This is why this thing is dimensionless. And again, this is a new building block. I have to put this thing inside to my theory with the other ones. Okay, so I have all these building blocks with this coupling. These are parameters. I call it coupling. And sometimes here is also, you can call it coupling, but sometimes you call it Wilson coefficient. Okay, we'll call it sometimes Wilson coefficient, but it's a coupling. Okay, the same way that you introduce the previous one and you put a coupling, you could call them also Wilson coefficients. Here, okay, we call it a coupling. I have to put a parameter that I don't know, and if I measure, I can know what is the value of this. Okay. This is over lambda, 1 over lambda, and now if I go along the lambda square, I have much more. Okay. But I think and I have to derive how many more. Okay, here it is, the list. The list, I think, is much simpler to get than when I was talking to you from the beginning, how many operators of dimension C you can write in the standard model. It becomes a long exercise, okay, to get them. Here is also some kind of exercise, but look to me much simpler. Okay, you have to go be ordered, but anybody can do it. Okay, you don't need to know any properties of complicated properties of fields to unread them and to eliminate them and to be sure that they don't get, because you have to look, for example, you start with how many 1 over lambda square, how many 3PTs I can write. Okay, and remember the 3PTs. For example, let me go slowly in this case. Okay. How many 3PTs? You can see that the only one you can write is okay. So it's 1 over lambda square. I have to put three angle brackets. Okay. Remember that it was told to you for probably first days that any 3PT amplitude can be written either in angle bracket or square brackets, okay? Not combination of the two, okay? So I know this has to be either brackets or squares, sorry, angle brackets or square brackets, okay? Here is angle, all angles, 3 of them. And I have to put 3 of them because divided by something dimension 2, the total is dimension 1, okay? And we're looking at 3 PTs, dimension 1. So this is the only way I can write something, okay? With a coefficient in front, of course, a coupling that they call Wilson coefficient. And now you can see inside, so I have 3 of them, but now the numbers, of course, cannot repeat because I put 1, 1, this is 0, as you know, because this is a contraction of spinors with the epsilon tensor, so you cannot repeat the index. So it has to be always simple, it's different, 1, 2, with the 3 and 3 with the 1, okay? Okay, that's the only possibility. And in fact, you could see that this is antisymmetric under the interchange of 1 and 2. And you learn more. For example, that if the 1 and 2 particles are the same, or the 2, 3 particles are the same, this should be 0, okay? Because if it's the same, I know I can by crossing, I can interchange them. The same particle, I have crossing, I can interchange them, and I should get the same. But if I interchange the 2 and 3, well, let me do like with 1 and 2. If I interchange the 1 and 2, okay, I get a minus sign from here, okay? Because this is unsymmetric. Okay, so it's telling me it should be 0. For symmetry, for the same state here, if I put the same state here, this should be absolutely 0. There will not. So for a photon, I don't have this kind of coupling. I only have a state, but I can have it for the SU2 gauge boson of the gluons, okay? Okay. And I don't know how
yeah, before you proceed, so you're assuming all the particles are massless right here, right?
Sorry, cannot hear well.
Massless.
The masses?
Yeah. Are you working in the unbroken phase of SH cross U1 or?
The masses are 0, yes.
Yeah, and another question is you mentioned that you don't need a gauge symmetry, but just using the field theory language, we know that in the standard model, we have fermions have different SH cross U1 quantum numbers, right? So how, could you explain a little bit how this quantum number enters in this gauge building blocks you are constructing now?
Okay, I don't understand it. I couldn't get it completely, the question. Are you asking about the gauge symmetry is not here? Okay, as you see here, I will not specify much the group. This is in general. I'm not specifying the global symmetries here in any example in any of these cases. Okay, but because this is of course is valid for the standard model, but is also valid for any other theory. Okay, what I'm explaining here, depending on the symmetries. Okay, what are the symmetries? The symmetries are global symmetries. What I'm using here, not gauge symmetries. Okay, so so in the case of the standard model, okay, I'm assuming that they have this. Well, I'm not assuming. In fact, this is another thing I could. I don't know if you think Juan explained to you that why it should be a global symmetry. You could say, don't put the global symmetry. The global symmetry is fixed. I don't know, explained to you before. Okay, for example, in this example, is very nice to see there is that the that I was explaining before to you. Okay, I don't know if he explained it, but I can say it again. The global, you have to, why you have to have global symmetries? Okay, when you deal with gauge bosons, okay, you have to use global, you have to have global symmetries because it's a condition that you have when you write this, when you start writing amplitudes. You see automatically here this amplitude. You see you have a 0. You can have a pole here when this thing goes to 0, or you can have a pole here when this thing goes to 0. So when you look at the poles, okay, and demand factorization, okay, as we demanded here, okay, we took this going to 0, and we demand factorization, okay. You see here I fix the coupling. This allows me to relate it with this coupling, but now everything here is fixed. Okay, fix the coefficient, but now when I go to the pole here, everything is fixed. So I have to demand proper This is a consistency check that I have factorization also. Factorization in the old channel that you find, factorization in the old channel force you to have these global symmetries, okay? If you have several gauge bosons, okay? So you don't have gauge symmetries, but global symmetries you are forced by proper factorization. That's the beauty of how you see that you demand the demand of having charts, conserved charts, okay? Demanding comes from proper factorization, okay? So Lawrence is restricting me this kind of here, but when restricting me here, this, no, because it's based on elicities, when I am restricted to be like this, now you see, I see poles here. There's a pole when this goes to 0 and another pole. And now proper factorization, the fact that I have two poles tells me that I have to demand proper factorization, okay, as I was showing here. So it means that when I go on shell, I get 3-point amplitudes I already have in my theory. Okay, so when you start doing this, you get that the gauge boson should couple with it should be in a theory with global symmetries. Okay, so you have to have global symmetries. If I have a photon, you have a photon, you should have a charge U1. If I have three Ws, I have to have a global SU2. Okay, if I have eight gluons, I have to have SU3. Okay, so my amplitudes have symmetries. Okay, no gauge symmetries, but have to have global symmetries. Otherwise, there is no proper factorization. Okay, into the different channels. Okay, I don't know if this was your question. Sorry, but probably you can tell me again. I don't know. So here I should have symmetries. Okay, as I was saying, and here I should write. I have to find different guys, as I said. Okay, and I have to have some coupling that is transforming as a triplet. Okay, because I have three guys here. So if you want me to put the invariant tensor, in this case will be FABC, that fulfill the Jacobi identity. Okay, because these guys are, I'm assuming they're triplets or octets in the standard model if they're gluons SU2, and now they have to have an invariant tensor, have to be this one. Okay, so I'm not putting this invariant tensor here. That is, of course, antisymmetric under ABC interchange, as we were saying here. I'm not putting this invariant tensor because I'm thinking I'll go probably later in more detail, and I think I put them, but this is more general. Okay, I'm looking only in the part on the kinetic part. The rest of global symmetry, that is related with global symmetry. So I should be sure. Okay, I should be sure that this any amplitude, of course, if I demand that my theory is symmetric, has some global symmetries. Okay. Should be proportional to some invariant tensor, okay, with the proper structure. So you were asking about anomalies? No, I don't know. No, sorry. Can you repeat probably, or?
Thank you. Yeah.
Should I go on?
Yes.
Okay. So now you can go on and you see that there's no more 3PTs. New 3PTs I can do a further 1 over lambda squared. But I now have many news 4 PTs. Okay, amplitudes with 4 states. Okay, these are this one. Okay, and now you have to go in order way. Okay, for example, if I have put it now, if this is dimensionless. Okay, as I said, an amplitude of states of 4 states is an amplitude is dimensionless. Okay, so you have lambda square. I can put in the numerator. I can put either 2 angle brackets, or as this one, these two, or 1 angle and 1 square. Okay, this is 1 angle and 1 square, 1 angle and 1 square. Okay. As I said, in a very ordered way, you can go on. Okay, and now you can put, you can have something like this. Okay, 1 2 square, 1 2 square, and this corresponds into 2 gauge boson and 2 scalars. or I can build, you see, in another way to the possibilities. Okay, I don't want to go beyond, but I mean, it will take you little time to start considering how many possibilities you can have. Okay, you can have 1, 2, 1, 2, 1, 3, 1, 2, 1, 3, 4. Okay, 1, 3, 4. I mean, and you automatically realize there are 3, 4 possibilities, and this could correspond to these amplitudes here. Okay, and more for the rest. Okay, and each of these new amplitudes, okay, there's a coefficient, a coupling, you can call it, a Wilson coefficient in front of it. Okay, these are 1 over lambda square. Each of these new amplitudes, so this is a new kind of building block. I can build amplitudes, higher point amplitudes with these guys. Okay, so I can take I can use it in my theory. Okay, at order 1 over lambda square and calculate different things. Okay, now there is an very important step that you realize that order 1 over lambda is, for example, I can have. I forgot to tell you something important. Sorry, yeah, when I was doing this. Okay, sorry. Let me go back to the standard model. It's a nice important property. I hope they will explain it to you. Is that I was calculating here plus minus minus, and you could ask, well, there is also minus minus minus. No possibility. Okay, you cannot build something with minus minus minus. Okay, so the fact that I told you the 3 PTs are fixed. When you try to build an amplitude with minus minus minus, you see 0. Okay. Okay. So this is what I wanted to say before. There is in the standard model, there is no amplitude with all fields with positive or negative velocity, except only one exception. Okay. So let me tell you afterward the exception. For example, if I'm looking here, I would say minus minus minus. This is 0, or a standard model amplitude with 4 vectors minus minus minus, 0, 2 vectors, and 2 Higgs minus minus 2 vectors. This is also 0. Okay, so it's a question of calculating. Okay, you see that all of them are 0. I don't know if you think explain to you this property. You can derive it by, you can use supersymmetry. You can use different tricks to see. There is not a fundamental principle behind it, but there's a very useful one. Okay, so this maximal helicity amplitudes. Okay, with all helicities minus 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 are 0. And there's in the standard model one exception. That is 4 fermions with minus, 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 minus. Okay, the total helicity is 2, because these are fermions, minus a half, minus a half, minus a half, minus a half makes 2. Okay, and you can have this exception in the standard model because you can get it from interchanging a Higgs. Okay, and this is a very important property, okay, that you don't see usually in the standard model. Okay, I mean, you don't see it you don't see when you do Feynman. When you project into helicity that you see that there are this tells you there's many zeros. Okay, many zeros when you calculate amplitudes, and this will be important when we do loops. Okay, so the general rule that you see is with this exception in mind. So except this case, the rest all amplitudes with all states with minus minus minus, or all states with plus 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 plus, the same of course, are 0. Okay, that's an amazing thing. Okay, that you see when, okay, so this is an important thing to remember, because this is in the standard model. Okay, and that's a good way, for example, to distinguish between in the standard model and beyond the standard model. That means lambda 4. Okay, for example, here we see that this is possibility to have two vectors with helicity minus, both minus and a Higgs. Okay, so I can have an amplitude here with two helicities, with all helicities minus. Okay, okay, so I can rewrite this amplitude at order 1 over lambda square. I can rewrite here also an amplitude with the 2 fermions minus and the vector minus. So all the guys that have helicity minus here. Okay, I can write it. Of course, if I have a lambda here, okay. If I don't have this lambda here, I cannot do it. But when I have a lambda here in the denominator, I can do it. Okay, so you see this important property when you go to order lambda square, and I have new possibility to add new building blocks into my theory. Okay, this building blocks define my theory. Okay, so either there are a minimal 3pt, 4pt amplitudes that define my full theory. Okay, everything with higher pt. Okay, any I don't know 10 particles coming, scattering, going to 10 particles by factorization should reduced to this one here, okay? So I can build up higher PT's amplitude, but when I go on shell, okay, and there is some poles, I go on shell, I have to factorize in order that things I have already here in my theory, okay? And you see now that how a complete change of what you have in the standard model. Okay, you cannot have this in the standard model. You can have a BSM. That's a very nice way to see BSM physics. Okay, just by looking at the elasticity of the particles. Okay, so this is a property will be important later. Okay, now let me make a little bit of contact with what you have done in effective field theories. Okay, with the standard model. You have been talking about operators. So the question is this, it should be, okay, these are amplitude that are of course related with operators that were introduced to you before. For example, this one that is 2 vectors and 2 Higgs, okay? And it's so simple as this, is related with an operator that you already saw in your effective field theory that correspond to 2-gauge boson F mu nu field strength and mu nu F mu nu with 2 scalars. Okay, if I go back to if I go back now to the dimension 6 operator list, okay, so I should see here, let me go, here they are, okay, a list of operators that contain field strength, 2 field strength for the B's, for the U1s, for the gluons, and 2 Higgs, H squared. Okay, so these operators, okay, will give you the amplitude, okay, so there is a not one-to-one correspondence. There's a correspondence, of course, of the as many operators you can write here as many amplitudes I can write in my case. Okay. So, sorry. Here. Okay, let me go back. And you can see this in this case. This is this. Okay. I am writing it here in a very generic case, in a very generic way. Okay. F mu nu 2 field strength contracted with a scalar. Okay. So again, in the case of the standard model, this can be the U1, the SU2, or the SU3, okay? And this is the Higgs. And I have to make it invariant under the global symmetries, of course, okay? And for example, this guy, that is the minus vector, minus 2 fermions and a scalar, can write it like this in amplitude corresponds, or can be generated from this operator. So you have this operator, this is the dipole operator, F mu nu, field strength, psi bar sigma mu nu psi and the Higgs. Okay, so if I get this operator and I calculate the amplitude, I'll get this amplitude here. Okay, but you see here you have to start in the effective field theory. You start with field, you start with operator, and after you have to do the effort to go to amplitudes, Feynman rules, and blah blah blah. Here you start already with this is the seat of all your amplitudes. Okay, there's a new amplitude you add in your theory. Okay, I don't have to go to fields at all. Okay, and now you could go on. Okay, so this correspondence between operators and amplitudes, I could go on. Okay, for example, this operator does only give me this, can also give me the equivalent one with squares. Okay, with the square brackets. Okay, that is the one with plus plus plus. Okay, there is another amplitude with plus 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 that I don't write here, of course, because it's just the trivial to go from all brackets to all angles to all squares. And there are others. Now I can go to 5 particles here. In this case, there is only one guy. Okay, with 5 particles, this has to have dimensions -1, and indeed this has dimension 1. It has dimension 2, so 1 minus 2 minus 1 total dimension. And with 6 particles, I only have one case of the 6 Higgs. Okay, where I don't have any, because the Higgs don't have helicity, so I don't have any spinors. Anything here, I have 1 over lambda square, so this is dimension 1 over mass square. That is the dimension of amplitude with 6 states. Okay, so I think the way of generating all these dimension 6 what is equivalent of dimension 6 operator, that are these amplitudes. Okay, so I call it in amplitudes 1 over lambda squares. Amplitudes is much easier. Okay, it's just I mean, everybody can do it. Okay, even if you don't know anything, what you are doing is just to put brackets or square and trying to put the states into it. Okay, in a consistent way. Okay. So I don't know if it's more clear, because now I go to loops. So I don't know if there are questions. Otherwise, I'll okay. So let me go to another important properties, as you probably heard from the lectures that you have on effective field theories, that I mean, one important effect is the renormalization. Okay, because let me go back to the effective field theories approach. Okay, as I was saying, this is an expansion, a Taylor expansion in fields. The leading order, you have the standard model, and after that you have here I don't put the dimension 5, you have dimension 6 operators, and of course these are what we call BSM. Okay, this is what right now we both experiment tell us that this is very good, works very well for all the experiments we're doing. Okay, we would like to see deviations from the standard model, deviation from this Lagrangian that will point out probably, I don't know, who knows, towards possible new terms. Okay, that could be classified as dimension 6 operators. Okay, things, new operators operated by lambda square. Okay. Now the question is that we are assuming that this operator is generated at some lambda scale lambda. Okay, here it is the scheme. Okay, and one of the properties that you have to do is, of course, you have to do the experiments that done at low energy. Okay, I'll be discussing electric dipole moment later on. Okay, but then experiment you have to go to low energy, to where the energy where you have to do the experiment, and we know that the couplings, when you don't measure that, these are generated at the scale of new physics, but now you have to measure the coupling at another energy. So usually at the W mass, if I do W physics, or even I can go down to the electron mass if I'm looking for the electric dipole moment of the electron. Okay, and the couplings, as we know in quantum field theory, change with the scale. Okay, and in principle, one of the properties in effective field theory is these operators can mix through quantum from loops. Okay, it can be one loop operator mixing, and this will mean that the physics coming in equivalent in my case. Okay, going back, it will mean that the physics coming from this amplitude at the loop level could affect the amplitude of, you see, the 3pt vector could affect you at the loop level, an amplitude that contains these guys. Okay, so they can be mixing at the loop level, of course, between one on the other amplitudes. Okay, as we will see. Okay, the evolution of the Wilson coefficients with the scale, okay, is characterized by what is called the anomalous dimension. Okay, this is the definition of the anomalous dimension: is the variation of the Wilson coefficient with the derivative with log of the scale mu. Okay, and it's important so to calculate this, how the we call running, how the couplings, as in the standard model, the couplings are not. We can determine the running of the couplings, and is the good way to derive the physics at different scales. Okay, I only have to evaluate, if I do an experiment at the mass of the electron, I have to only to evaluate the couplings at the scale of the electron mass. Okay. Okay, and so this is an important piece in effective field theories. Okay, to know how this thing. Okay, I want in amplitudes, similar thing is going to happen, and I want to derive how to obtain these ones from on-shell quantities. Okay, this is probably the second part I want to derive here. Okay, let me say something before. Okay, this calculation of the anomalous dimension that I don't know will be explained by other lecturers here. You can do it in the standard model. It has been done. Okay, how these operators here mix. Okay, the loop level. Okay, how and one of the properties was found is that there are many non-trivial zeros in the anomalous dimensions. Okay, and it was a kind of surprising. Okay, because these zeros were not expected. It's not, of course, when you do a calculation, a loop, you put the Feynman diagrams, calculate. You never know a priori the result. You expect to get a number. When you get the zero, usually you expect, oh, there was a symmetry. Oh, this is not generated by a symmetry. There must be something. And these zeros, people were not finding any symmetry. Okay. People were not finding why this amplitude was 0. I don't know if I have examples here. Okay, I'll tell you some examples, yes, later. Okay. Well, let me skip this. This is how many zeros were found. Okay. That, so for example, this operator could not mix with this, and this operator could not mix this, okay, because the anomalous dimension was 0. So there was no mixing between through the anomalous dimension between this operator and another of these operators, okay. But it happened to many cases, okay. I'll concentrate here in a case that is important, also for phenomenology as a motivation, okay. Why we do all these things? It's because we want to find new physics, for example, in experiment. For example, one of the most beautiful example is what I was saying to you, the electron electric dipole moment, okay, that we measure, and we have a very strong bound. The electron electric dipole moment has to be very small, okay, 10 to the minus 29 e times centimeters. And if we have new physics, of course, we can generate it even at the two-loop level. If I put lambda further, if I put something like two-loop level here, I have a contribution from new physics at the two-loop level. I can estimate what is the, today with this bound, what is the bound on lambda, and I get the lambda should be larger than 3 TeV, okay? So we see that this is a very good bound on new physics, okay? Because this measure tells me that if I have new physics at 3 TeV, below 3 TeV, I will see it even if they enter at the two-loop level. Okay, there's an estimate that tell me this. Okay, and now question. So I'm trying to understand what is in the standard model. Okay, in the standard model, this electron electric dipole moment is very small. Okay, it's very small. I forgot the number, 10 to the minus 33 or 34. I forgot now. Extremely small as compared to the present experimental bound. Okay, and so I expect that new physics can affect me. It's a very clean observable. Okay, the contribution from standard model is very small. I hope dimension 6 operators can affect this quantity, this physical quantity. If I see deviation, if I see non-zero, this is a bound. If I see non-zero electric dipole moment, it will be a proof that I have new physics. Okay, so it's important to see how the operators mix. Okay, and now, yeah, here is to show that we're looking at this thing, and there is only few operators that enter into renormalization of the dipole operator. Okay, these are the dipole operators in your list of dimension 6. Okay, this looks like something like W mu nu, the lepton standard model. Fermion sigma mu nu psi and a Higgs. Okay, these operators have this dipole operators, and they contribute if the coefficient is complex. The Wilson coefficient is complex, contribute to the electric dipole moment. So I would like to see other operators. How the other operators? Okay, yeah, probably I hope to have the same notation that you are using in the lectures, but if not, doesn't matter here. The point is to see. To show that there is a possibility many 59 operators can mix at the one loop level here, but at the end it's only 2. Okay, so there are many zeros, only 2 of them. I mean, only 2 types, these ones and these ones, can mix at the one loop level with this one. So the one. Okay, here is an example. Okay, this is to show that there are many zeros. Okay, this is one example of one of the zeros. Okay, for example, if you look at this dimension 6 operator for fermions operator. Okay, here it is, contribute for fermions, and I close the loop. Okay, I have a contribution to the dipole, to this operator. Okay, to fermions, a vector and a Higgs. Okay, Higgs, a vector, and 2 fermions. Okay. Now you calculate this. This a priori no reason to be 0. Okay. But at the end of the calculation, okay, from Feynman, okay, this is the Feynman approach to calculate this. At the end of the calculation, you get that the contribution to the anomalous dimensions of this guy is 0. Okay, so there is no for fermion contribution. There's no for fermion contribution to the dipole. Okay, and like this, there's other examples. Okay, there's many examples where you calculate this thing, you expect the you do the loop. You see when you do loops, you don't know what to get. You have to. Of course, I know there will be a coupling here. I can estimate a little bit. Okay, there will be some loop factors, things like this. But at the end of the day, you expect to come a number. This is why you have to do the calculation, the tedious calculations, loops. And the number, okay, in this case comes out to be 0, but there is no obvious. You start thinking there should be some symmetry, and you don't see it from the Feynman approach, okay? Let me skip this. As I was saying, this is an example. Okay, so now let me do it now. Okay, try to get this thing, how you get it from the approach of amplitudes, okay? Because we know how to do it from Feynman, okay? You have your Lagrangian, you know how to derive the Feynman rule. With the Feynman rules, you put them in, and now there's a clear algorithm of how to calculate loops, one loop, two loop. This with fields. This is when you study effective field, quantum field theories. But here we want to do the similar thing. Okay, so back to our, sorry to go up and down, but that's probably. Okay, so I have this amplitude I was saying that can mix to other ones. Okay, okay, so I can have this coupling can enter. This coupling parental can enter into this thing. Okay, and I would like to, in some sense, to calculate also this coupling. Also, they run. So I would like to calculate in the same way they calculate for the operators. I want to calculate how these couplings evolve. Okay, run depends on what is the Romantian group equation of these couplings. Okay, of all these ones. Okay, so this is also again an anomalous dimension for this. Okay. So this is equivalent to calculate amplitudes at the one loop level. Okay, so you have the level part, okay, for the amplitude AI. And now, as I was saying, I want to say how another amplitude AJ, okay, can enter here, okay, and through a loop can affect an amplitude that is AI, okay. I'll give you some example, okay. This is probably too generic. I'll give you more particular example to understand it, okay. Okay. And because in this amplitude, as I said, okay, let me write it like here, I can write it here. In this amplitude will correspond, for example, to the dipole, there will be a coupling here. Okay, times, for example, let me put one I will use later, the amplitude of okay, let me do it later. Sorry, let me not start here doing it. I'll do it later. Okay. So the idea to, okay, so it looks like here, when we have learned to do loops, it looks like here you have to go off shell. Okay, we know how to do this loop by going off shell. These particles are off shell. Okay, and we know how to do this. I mean, this is a quantum field theory approach, Feynman approach. Okay, what they call Feynman approach. Okay, it's approaching quantum field theory where to, and we know that this is in this process, these particles are not on shell. And now it looks like if we start everything on shell, there's no possibility to get these loops. Now the approach that have been understood that how to go also to do these loops on shell is the following. Okay, so I'm interested in this loop, this contribution. Okay, and as I said, it looks like particles appear here of shell. Okay, now the idea is the following: at the loop level, okay, any amplitude can be written as a reduction of what is called the Bastardino-Bellman integrals. Okay, you can write any amplitude as some coefficients that depend on the kinematics times some integrals I2, I3, I4. Okay, that are that are integral on the momentum that contain two. Okay, that I write represented here, that contain two propagators. Okay, so let me write it here, very to clear. This I2 is something like D on the momentum Q, something like dQ at the dimensions. Okay, and contains two propagators, P1 times P2. Okay. Okay, and now this is a decomposition where this guy is dQ, and this contains integration over. Okay, contains three propagators, P1, P2, P3, and I call this bubbles, okay, contains, because I can write it like this, I can draw them like this, okay, as I say, contain 2 propagators, okay, you can see here, or triangles, we can write it like this, contains 3 propagators, okay, so 1, 2, 3, or 4 propagators, I call it boxes, okay, for propagators, plus some extra things that are called rational terms that correspond to constant terms, something that is not related with this. Okay, some are not, can be power, I mean, can be things depending on the kinematics, on so p squared, p4, but they are not something like has no prop 1 over p squared like we have in here. Okay, does not contain these integrals. Okay, and this can be shown that you can always split your amplitude as a function of this type of integrals. Okay, now, let me eliminate all these things. Let me see if I can. Oops. Okay, back. Now, I'm interested in renormalization on the effect of renormalization. Okay, to get how the couplings depend on the constant, and I hope you remember from quantum field theory how you do it. You look for log divergence. Okay, you log divergences, and that have to cancel by a counter term, and this counter term tells me the coefficient of this counter term tells me what is the anomalous dimension. Okay, so here I only have to look for the divergent part, and the divergent is obviously can only come from this guy. Okay, UV divergent because this is an integral d for p by 2 propagators. Okay, so the d for something like here with p1, p2, with two propagators that has dimension p squared. So okay, the only one can be divergent, logarithmically divergent is the guy. Okay, the other guys can be UB convergent. Okay, because you have much more. The denominator you have more momentum than in the numerator. Okay. So the anomalous dimension is related with this coefficient here. Anomalous dimension are C2. Okay. So I want to get this C2 coefficient here. Okay. Now, how I get it? Of course, I can do the loop, but now the trick is the following. If I want to look at this amplitude, and now I know that there's there's several ways to look at this. I can look at for example, this is a complex amplitude. Okay, so I can look at the imaginary part of this part and relate with the imaginary part of this part. Okay, this is equivalent to consider what is called a double cut that correspond to taking this loop and cutting 2 internal lines. That means putting 2 the states here on shell. Okay, putting these guys on shell. Okay, this is in this way you get the discontinuity of this amplitude, or if you want also the imaginary part of the amplitude. Okay, but in general, I can say that that's okay. There's a well-defined way to define here what it means represent a double cut. They correspond to put in it can be, there are several of them. You can cut this and this, or I can cut this and this, or I can cut this and this. There are many double cuts here. Okay, but this is one of it. Okay. If I do the double cut here, correspond also here on the other side, on the left, on the right, to do also double cut. So here they are. For double cut, there is only one I can do here in the bubble, and in the triangle I can have double cut like this or double cut like this. Okay, and here this also the same. Here I have several for the box. Okay, now if I do the double cut, as I said, in this case, I am putting the internal particles on shell. Okay, and now the diagram here looks on the left looks very nice. This is just what a 3-level amplitude, this one, times another 3-level amplitude on the other side, And remember, when I do the double cuts, and you look in any book of quantum field, textbook in quantum field theory, this is putting the particles on shell, but they have to integrate over the phase space. Okay, so you have to put, this is equivalent to say that I have to calculate two amplitudes and integrate over the phase space. Okay. On the other side, what I have, okay. Let me skip this, but I can prove that it can be proven that the contribution from these boxes, from these triangles and these boxes, okay, this contribution gives 0. This is due to, this is a tricky thing about the infrared divergences, okay. Let me assume, you can assume for a while that there is no infrared divergences, and now you can prove exactly that they should cancel, okay. If there are infrared divergences, you have to subtract it, okay. There is a very easy way to you have to subtract the infrared divergence, because you know what they are, and you know that you can define quantities infrared safe, okay? So there is some subtlety with infrared divergence, but let me skip it, okay? For simplicity, if you want, you can say that there's no infrared divergences for the examples I consider, but if you want to put infrared divergences, only have to do a little bit more of exercise and subtract them, okay? But what can it be shown that these contributions are 0? So that only remains these things. Okay, the bubble. When I cut this 0, 0, and of course there is no cuts here. Okay, there's a rational term. There's no contribution from here. Okay, if you want the imaginary part, there is no contribution to the imaginary part here. So I only have the cut. Okay, so this gives me the integral of the cut, give me a number, and I am so when I equate this, I'm equating now this to this. Okay, the rest are 0. Equating this to this with this thing is a well now defined quantity. So in some sense now by doing the two cut, I'm picking up this thing. So I'm picking up this thing, okay, picking up the C2 that we said before, that is the part I wanted, okay, because this is only, this guy is the only guy that is UP divergence, and the coefficient in front is what we define the anomalous dimension. So I can write an equation that looks like here, down here, like this, okay, where the anomalous dimension, these C2 coefficients, okay, this is one cut, so I'll have to do for all cuts possible 2 cuts. This, all cuts, okay, because I have to collect all the C2. There is a sum over bubbles. There are many bubbles here, okay, because many integrals of this type after the loop. Okay, so this anomalous dimension, I write it here. This part is written here. Okay, the anomalous dimension times the amplitude I'm calculating, it has to be equal to this part. And this part is here. Okay, so what is this? As I said, this is a product of 3 level amplitudes. This, I call it this. Okay, that involve, okay, let me say another thing probably I was not saying. I'm interested to calculate at order. I'm interested to calculate, as I was saying, the mixing between dimension 6 operator. Okay, for example, I was discussing this case here. Let me go back. Okay, so I'm calculating this contribution to this operator that is 1 over lambda square order. Okay, so here I have only to look for 1 over lambda square. I cannot put 2 1 over lambda square. I have to put 1 operator just on dimensional counting. Okay, to generate something that goes like 1 over lambda square in the loop, I can only put an operator 1 over lambda square. I cannot put 2 of them, otherwise it will go like 1 over lambda 4. Okay. So when I go here in my formula, I have 2 types of amplitude. One will involve this one dimension, this extra 1 over lambda square. This is what I wrote here with the hat. And the rest will be just a standard model amplitude. Should not contain any of this 1 over lambda square. Okay. Okay. So this is a product of something like involving 1 over lambda square times some amplitude of the standard model, and I have to sum, I have to integrate over the phase space. This d-libs means Lorentz invariant phase space integration. Okay, and as I said, I have to sum over. It will contain all the cuts, so I have to sum over all possible amplitudes. Okay, here. So this is an example of this amplitude. I will have another one. So they cut like this, and I have an amplitude like this, and an amplitude like that. Okay, so there are different types that you'll have to sum over all of them. It looks like complicated because the formula have to be generic, but I'll go to the particular case and I will see that this is very simple. Okay, and the relation is exact. You can calculate exactly sines for pi, blah, blah, blah. Okay, let me go to the example because otherwise one gets confused. Okay, and the example is one I was telling you, for example, inspired by the electric dipole moment of the electron, okay? Also, it's similar to the G-2 of the muon, okay? If you think there is some anomaly in the G-2 of the muon, you are interested to see if there are no physics there. So this is the magnetic dipole moment, the G-2 of the muon. Is the magnetic moment I was talking about. The electric dipole moment is coming from the same operator, okay? Magnetic moment, if the coefficient in front of it is real, if it's pure imaginary, if it's imaginary, goes to contribution to the electric dipole moment, okay? So, but the operator is the same, is this operator. I'm interested to get renormalization from other operators, okay? Okay, now in amplitudes, as I was saying, this thing is related with this amplitude, okay? Correspond to here I have a gauge boson, to fermions, and a Higgs, okay? And as I was saying, this is an amplitude with minus, minus, minus. Okay, and we're interested to look at the contribution to it, okay? I was telling you before, okay, that in principle, okay, I want to discuss here that there are the zero, okay? I want to see first the zero. After that, we can see what is the contribution, but first let's see why you get zeros, because now you can say one can be able to understand the origin of many zeros, okay? So let me go to the example I was telling you before, okay? You look for fermion operator, so this is an operator that goes 1 over lambda square, okay? I didn't put it here, but okay, in your Lagrangian will be dimension 6 operators, so 1 over lambda square, and I put it here, 1 over lambda square. Okay, this operator for fermions, okay, close, and I have a contribution to this guy, as I was saying. This is from Feynman. Again, if I do it for Feynman, I give you 0, okay? But I'm looking at the diagram in a different way. Okay, I'm looking at the diagram like cutting it, okay? If I cut here, I have 2 amplitudes, okay? So what I'm calculating with the formula I was showing before, here is much simpler, is this amplitude times this amplitude, okay? And integrated over phase space, okay? So I'm calculating this following process, is an on-shell process. These 2 particles can come, scatter, 2 particles here that ray scatter and give me this, okay? So it's a three level process, okay? So the loop, due to the technique of looking at the 2 cuts, okay, that I was saying, okay, this technique of looking at 2 cuts the loop can be thought about, especially only the anomalous dimension, okay? So I'm looking at the anomalous dimension. Otherwise, there can be other, okay, let me go back, okay? What I'm saying here is only to get the anomalous dimension, the divergent part, the C2s, okay? The loop give me, is richer, there are other terms, okay? I'm only now telling you how to get this, okay? Have time I'll go through, but I don't think I'll have time to tell you more how to get the rest, okay? But now it's okay, good to, the normal dimension is quite simple. Okay, so the formula tells me I have 2 3-level cut, okay? This very physical process. This guy enters, is scattered, okay? I mean, sorry, this guy is scattered and there is scattering to the other 2, okay? Okay, that is represented like this. This is integral phase space integral of these 2 amplitudes. Now, this amplitude, of course, is very simple. This is 4 fermion interactions. Okay. If I rewrite it, I can even rewrite it for you here. This is something like 1 3 2 4. No, sorry, sorry. This is the take it back. Take it back. Sorry, take it back, because this is the amplitude with 2 fermions are in helicity minus, and the other 2 fermions are in helicity plus, okay? This is the amplitude corresponding to this thing. You see here, the helicities are not very clear represented. The amplitude is very much easier. Okay? If I tell me this, these are 2 with plus and 2 with minus, 2 with minus and 2 with plus helicity, okay? Now, the key point is that, okay, I didn't write it here. Okay, so now I should write it, that this is an amplitude, because, okay, from here I generate an amplitude. This is minus a half, okay. Okay, incoming. Okay, let me go, and this is a half plus a half plus 1/2. Okay. Okay, that it should be becomes a particle plus a half. Okay, in the other it should is equivalent here. The particle is incoming in the other diagram with minus a half. Okay, the conservation of helicity. Okay, so I'm saying if I look at this guy generates this amplitude. Okay, with helicity is minus minus plus plus. Okay, and now if I have to have a contribution to this thing, I see that I have to have an amplitude with, okay, this one with minus, minus, minus. Okay, all helicities are minus. And we already said this is absent in the standard model. Okay, there is only one exception when we interchange the Higgs, that is not this one. Okay, so you start seeing that the zeros, the many zeros you found when you do Feynman diagram, this is hidden in the Feynman diagram, this information. This is possible because I am able to calculate this by cutting, and now I do 3-level amplitudes. I now use the properties of the 3-level amplitudes of the standard model. That up to one exemption, okay, all the amplitudes with all the guys in the amplitudes coming with minus, 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 or all the guys coming with plus, 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 plus are 0. Okay, so I know this amplitude is 0. Okay, so I know this anomalous dimension is 0. Okay, so this doesn't exist. And like this, I can go on with many examples. Okay, just this property that except one exception, this is a very generic property. I can use it almost always when I have minus, 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 except when the exception I told you, the others are 0. Here I have another example. For example, for you is like if I want to see how these coefficients, this operator, okay, renormalize the operator, the b mu nu h square operator. Okay, what is the renormalization of this operator to this one? Also is 0. Okay, and in amplitude the same as exercise you can see. Okay, because I have this is the loop. A priori you have a loop. You calculate, it doesn't look like should be 0. Okay, this is the loop. But so I'm missing some information here. Yeah. Okay. Some information. Here's the operator want to generate. So I rewrote it here. And now you can see that this is if I cut like this, these operators, this loop. Sorry, this is of course helicity zeros. But this amplitude. Okay, here the operator is related with the amplitude. Okay, that is the vector. There's an amplitude we defined before, vector minus Higgs. Okay, with the vectors are into equal helicity, -1, -1. Okay, and now again. Okay, if I cut the diagram, I have to have in the standard. This is the coming from this dimension 6 operator. This diagram, this amplitude, and this amplitude, what is again? It's a 3-level amplitude, 2 scalars going to 2 vectors, but the vector should be in helicity minus. And again, this does not exist in the standard model. Okay, all the states are in minus minus, or 0 doesn't count. 0 for the scalars, minus minus doesn't exist. Okay, so the absence of this. Why this diagram doesn't give you a contribution to the anomalous dimensions of the Wilson coefficient here. There's a Wilson coefficient here. Is because I can do this. I can rewrite it with this formula, correspond to 3-level amplitudes, which one of the amplitude is always absent. Okay. 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 So this is about the zeros, but of course you want also to calculate when these things are non-zero. Okay, and the interesting thing that when you do it in this using this on-shell method is that you have relation between amplitudes that between renormalization or loops that you didn't expect it. Okay, here these two examples I like to show. Okay, Okay, now is when we want to see for non-zero result. Okay, so you can get zeros because it's easy. You don't have to do the calculation. You just see, you don't see the amplitude. You don't have one of the amplitudes. But let me show another example where a non-zero. For example, this here is a diagram that you calculated. Again, this is a contribution not to the. We're saying is zero when it's this type of operator, psi bar. Oops, the bar should be on the bar. This is psi bar gamma mu psi. But when you have operator psi bar psi square, this contribution to the dipole is non-zero. Okay. So now you do this diagram with this operator, and surprisingly from Feynman, from the loop you see is non-zero. Okay, the previous one was zero. Okay. So this is non-zero, and here is another contribution to the dipole. Okay, again, to fermions with helicity minus and coming from this operator, f squared h squared. Okay. So you look at this, so you do the Feynman approach, you have these two types of loops, and they don't look at all similar. It looks like what I have to do. I have to do this calculation on the loop, finish, and start another one, okay? Doesn't look any similarity, okay? But let me do it through the trick, the formula I was showing, okay? Here is sketch in the sketch way, okay? That the anomalous dimension can be calculated by a phase space integration of three level amplitudes, okay? That again correspond to, if I want to look it from the loop, correspond to like a cut here and having two amplitudes, one here and one here. Cut here, I have now the product of two amplitudes integrated over phase space. And now if I do this, now I see the similarity, okay? Because the amplitude I need in the standard model, okay, is exactly the same. This is two fermions. Okay, this is two fermions, a vector and a Higgs. That the one I told you at least I sketched to you how to derive at the beginning. Two fermions in the standard model vector boson and a Higgs. And here is the same. Two fermions, a vector boson and a Higgs. Okay. Of course, here is in a different way. It was some of the particles were inside the loop, but now when I do the cut, this is a three-level amplitude. This is the same three-level amplitude here and here. Okay. So you see that the renormalization back to here looks like surprising, that the renormalization of these two operators to the dipole, the seat of this renormalization is coming from the same amplitude. Okay, so once I calculate one amplitude, this amplitude I have bonus, I have the two anomalous dimensions. Okay, of course I still have to do an integration, but the integration on phase space is easy. Okay, so the question when I want to show here is that of course all calculation is useful. Okay, when you had one, now you can use it for the other case. Okay, I had the derivation. I don't know. I have some time probably. I had the derivation here of the case one is non-zero. So let me see if I have it. Probably to show the flavor when the calculation is non-zero, how it goes. Here it is. Okay. The same as I had before. Okay, this is the same formula. So the anomalous dimension of the amplitude, now written in amplitude of the dipole contribution, that is this amplitude, is equal, okay, to what? Some integration, phase space integration of two amplitude. This one, of course, this is trivial. This is just the amplitude of this one over lambda square. Okay. I mean, I don't have to calculate anything here. Okay, I have the amplitude from the beginning already. I defined it at the beginning, dimension 6, and the only thing I had to calculate is the standard model amplitude. I calculated that you can see this is minus, minus, minus. Now this can be plus, plus, minus, and this amplitude exists. Okay, and we calculate, this is exactly the one we calculated before. Okay, vector, two fermions, and a Higgs. Okay, where the helicities are changing in order not to be zero. Okay, so this usually you see why you have a contribution, because this amplitude involves minus, 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 minus. Okay, if in both like before minus, minus, plus, plus, this will have to be minus, minus, minus. It doesn't exist. Okay, so this is trivial amplitude, and here the one we calculated already, and I have to integrate over phase space. Okay, let me show here how to do it, because the phase space integration is also very easy. Okay, because remember some of the states here, I put it like this is exactly, I put the internal state with a prime, 3' 4' prime. So there's some 3' here, 4' here coming from these guys. Okay, and the question is how to do this integral. Okay, there is very simple thing, because you know you can relate spinors, internal spinors as a function of 2. Internal spinors can always be related with the external spinors. Okay. And because I can take a basis of spinors, okay, that these are the external one, and relate internal spinors as a function of these two ones, 3 and 4, that are external. Okay, so this tells me how to relate this 3', 4' as a function of the 3, 4 that are the externals. Okay, and this there is a rotation like this. Okay. Okay, and now the phase space is an integration over these angles, cosinus of theta and azimuthal angle phi. Okay, so if I can do it different ways. Okay, but there is a way to do it. Okay, relate this internal spinor with a function of the external spinor with some rotation, generic rotation. I plug it here and I integrate over the phase space. Okay, that's very simple. Okay, so I'll get a coefficient here. This coefficient here will come here. And the rest is just integration over some angles. Very simple integration over some angles. Okay. Here I already abstracted only the anomalous dimension, so I divided by these things. That is a non-trivial check. You should see that when you do this thing, you play it here. The non-trivial check is that what remains should be having the same, exactly the same structure of the dipole structure. Okay. It cannot be any other thing. Okay. Okay, so I can eliminate it here, and from here, okay, after this subtraction, I will come also 3, 1, 3, 2, and will eliminate it. Okay, so the normal dimension will remain to be some simple like this. I do this integration and I get the result. Okay. So that's to show when it's non-zero. Okay, so sometimes this is zero because the amplitude is not there. When it's there, I have to calculate the amplitude and plug it in here. Use some relation between internal spinor and external spinor, put it here, and that's it. Okay, so in principle, the calculations are simple to do, even when they are non-zero. Okay, and as I said, when I have, I was showing you this calculation. Okay, when I have this calculation, this is a very simple one also, where I have, because I have the same amplitude, the same standard model amplitude. Okay. And these properties of renormalization between at the loop level between amplitudes, that is has some pattern. Okay, for example, all this. Okay, at order over lambda square, I was saying at the loop level, these amplitudes will mix. Okay, but the mixing always comes from one of the standard model amplitude alone, only one of them. Okay, so once you have this amplitude, when you calculate, this is the one we calculate to fermion vector and a Higgs. We're talking always about the same. This example, when you know this, you know how this, you can calculate the mixing between this and all combinations. Okay, and similar to other amplitudes. For example, in this type of amplitude, you see you need only this thing, 2 fermions and 2 Higgs. Okay, that's the only amplitude you need to calculate in the standard model, the level to see the normalization of these things. Okay, it's probably not easy to see. Okay, I'm telling you. Okay, you have to see that really when I want this to enter and mix and generate this one, okay, this amplitude to generate this one, I see that can only proceed through this standard model amplitude. Okay, in the formula, no? The formula I'm writing all the time, the formula that tells you that where it is. No, here it is. For example, the anomalous dimension is a phase space of some dimension 1 over lambda square amplitude times some standard model amplitude. It's a question of matching the internal states. Okay, the internal states, of course, have to be the same. Here, this internal state, of course, is the same here. So this internal state are the same here. Now, only briefly, okay, even that you cannot follow probably the derivation. The fact that you are now on shell, dealing with amplitudes on shell, you can also do partial wave some kind of angular momentum decomposition, partial wave. All amplitudes, of course, can be decomposed as a partial wave decomposition, okay, and written as a partial wave that correspond to amplitudes with definite angular momentum, okay, so of the incoming particles, okay, so you can say this is here it is an example, okay, it's the same example, the dipole, okay, two electrons here, they have an amplitude of I don't talk here about the electron, but two fermions coming in with a Higgs, interacting with a Higgs and a vector, okay, and I can do a partial wave decomposition, okay, as in the, let's say, in the S channel. Okay. So, and now it means that, and what happened here? If I do this partial wave, you will see that this amplitude, the electron, the incoming particles can only be in some angular momentum, well-defined angular momentum, even that in general, an amplitude is a sum over partial wave of all momenta. In this type of amplitude, okay, it's easy to see by calculating this AJ that only contributes to the A1, to the with J1, okay? Because this is easy to see that probably don't have time to see here to explain that these guys have to be in angular momentum 1, okay? So it means that this has to be angular momentum 1, and of course, the incoming momentum 1, the amplitude the outcoming has to be also in angular momentum 1, okay? Okay, so what it means back to the previous case I was discussing is that this has to be, as I was saying, this if the incoming or going has to be angular momentum 1, it means that I only need not the full amplitude of the standard model I was telling you before. We had to calculate. I only want the partial wave in J equal 1. Okay, this amplitude in the standard model has a partial wave decomposition that where, of course, there's contribution to all J's. The amplitude has contribution to all J's. Okay, and this is the dipole. The dipole only have contribution to J equal 1, but the generic amplitude, okay. Okay, so this is the dimension. Sorry, this is the 1 over lambda square amplitude. Okay, this is the here again. This is the again. This is the 3, 1, 3, 2. Lambda square amplitude. Okay, when I look at this amplitude, okay, this is only coming J equal 1. Of course, if I look at the generic amplitude, they can be all J's. But to calculate a contribution to this dipole, since these states are in J equal 1, I only need the J equal 1 partial wave of this amplitude. Okay, so I only need this number. Okay, so the anomalous dimensions, okay, that looks when you do loops, I don't know, any number can appear, looks like it's always proportional. Either this one here you appear, also this one here appear, should be only proportional, not to the, you don't need even so much information like the full standard model amplitude is here, but only its partial wave J equal 1, okay? And in fact, the fact that this J equal 1, it means that, of course, the incoming, this states an equal J equal 1, this states an J equal 1. And there you can see in other examples that there should be, you say, conservation of angular momentum, of course, give you some angular momentum selection rules. Okay, so this is the J equal 1 here. These guys here in the middle should be J equal 1. And now if you have an operator here that the states are, these states, okay, these states here, the internal states are not in J equal 1, and different than 1, you will not have contributions to here. Okay, so you know that this internal state should be in J equal 1. Okay, also because this is an amplitude. Okay, so you have J equal 1 coming in, J equal 1 coming here, J equal 1 here, J equal 1 in the final ones. Okay, so there is some angular momentum, this angular momentum conservation that tells you, and again, selection rules. Okay, so amplitude that give to J equal 2 cannot contribute. So in many cases, these anomalous dimensions can be written not generically. Okay, this is not a general, but many examples can be written as a product of partial waves. In some, a priori should be sum over J, but as you can see, in many examples, it's only by 1j. Okay, in the previous case is j equal 1. Okay. So these are very simple formulas. Okay. So saying what is happening. Okay, let me go back to tell you why this thing, just get a flavor of what is happening is that remember you have an integration over phase space. In some sense, this integration over phase space, what it's doing is selecting to the standard model the j equal 1 in this example, of course. Another example with a different j. Okay, so this phase space integration is telling you, oh, here you have to select the j equal 1. Okay. So at the end of the day, you know, this, if you know this, you go directly to get the partial wave j equal 1. Okay. Okay. And now there is no phase space integration. It's already the phase space integration is projecting you into some definite j. Okay. So as I was saying, here is an example of many anomalous dimensions that are related to the same partial wave of the standard model. Okay, so this is a type of relation. I understand you don't follow here what it is, the detail. The only thing is to say there are many different anomalous dimensions that looks very different from the Feynman approach, but they're proportional. Okay, here's the exact calculation. Okay, it's proportional to the same number, to the same standard model j equal 1 amplitude. Okay. And also I don't want to go through it, but this is very nice, especially for gravity. These approaches are very nice for gravity. Gravity, if you do Feynman calculations, kind of a nightmare, okay? Because you have a graviton with many h mu, with many mu's and nu's they're contracting, only getting the Feynman rules are complicated. However, we're doing in amplitude, this is a very simple, and you have properties similar to this one. You can see renormalization. I only want to say here that as you do for gravity, you see that, for example, the mixing between different the anomalous dimension mixing different amplitudes, what would be equivalent in effective field theory, mixing different operators is coming, for example, in this case from the j equal 2. Okay, so if you know the NGR, the j equal 2 numbers, okay, you can calculate the partial wave in j equal 2, these are two numbers. Now you have many of different anomalous dimensions. Okay, I don't want to give more details, just to say that this is like this. Okay, and by the way, this is not a generic. As I said, this is not always possible. This decomposition in partial wave. Okay, this is an example that you can look a little bit here. I want to mention where it's not so easy to, because you get logs and more complication, okay, in this kind of calculation. Okay, for example, how the W3 enters into the dipole. Okay, W3 is the in operator is this field, the one that we were discussing before, for field strength. Okay, F mu nu, F, okay. And now in the case you see the partial wave decomposition is not very useful. You can do it, but it's not very useful. Now also now only brief things only here now to mention that of course you can go to beyond one loop. Okay, it's possible, little bit more complicated. Nevertheless, it's sometimes simple. For example, we were calculating here in this paper the two loops for the mu gamma. Okay, coming from this type of operator. Okay, so I'm writing in operators, but of course there is a corresponding amplitude. And now it will look like from normal rules that this is very complicated, but we were showing that this is very simple in amplitude. You have to calculate. You can also get two loops from two amplitudes. Okay, you have to calculate two tree-level amplitudes. This 1, 2, integrate over phase space now of 3 states, and also giving you the anomalous dimension. This implicitly happens when so it happens when this operator cannot enter at the loop level. Okay, this operator, for example, you can show cannot enter to mu gamma at the one loop level, can only come at the 2 loop level. Okay, and when this thing happens, the 2 loop level, if you don't have one loop, the 2 loop level is usually very simple to calculate also from 3 level amplitudes. But in general, not. Okay, in general, you can have something like 1 loop going to 3 level, okay, to give you the 2 loop contribution. Okay, so it's not generic, this thing. that you can be simple. So I'm saying in cases where you have the mixing doesn't appear at one loop, you want to calculate how it appears at the two loop level, still you have the simplicity of writing this complicated two loop from a product of two three-level amplitudes. There is a final issue, but I don't know. Probably I think because I will stop here, leave it here. What about the finite pieces? Okay, I talk about renormalization effects, the divergences. Okay, how to select the divergence, but you would like to calculate finite pieces. Okay, and now the method can also be useful. In particular, here we show, for example, that there was a paper by these people showing that, for example, in a theory where I calculate the contribution, final contribution G minus 2, for example, coming from a singlet, massive singlet and a doublet, extra BSM, to put extra particles to the standard model. For example, let's say there is a massive singlet and a doublet, okay, and now you have this loop contribution to the G minus 2. And they were showing that this is at order 1 over m squared cancel. So there's a cancellation at order 1 over m squared, a leading order. So you have to go to subleading. Okay, again, you calculate the loops and now you get 0 at order 1 over m squared is 0. Okay, and now here again, you can do tricks, and it was possible to show that this is coming from a product of two amplitudes. Okay, it's only to flash you the idea that can also be useful here. And showing that this amplitude in particular, now you can see the amplitude, it was very simple to show that it had a property that it was odd under the interchange of the singlet with the L, although you had possibly two cuts, okay, two contributions that were even under SL, okay? So it was easy to see that the amplitude was odd under the interchange of SL, but you have two contributions that were even under SL. So there was a clash between even and odd, that it was the reason why they should be, the total should be 0, okay? Order 1 over m squared. Okay, so also again, the fact that you can look at this as a product of two amplitudes was useful to tell you that these kind of things can be 0. Okay, and you could find other zeros with using these techniques. Okay, also for finite pieces. It's a little bit more complicated. Okay, because I have to go back to the origin of everything, that is this decomposition here. Okay, and I showed to you that when I was doing double cut, I was able to pick up here. But for the finite piece could come from here, here, and here, okay, and even from here, okay. But here we were able to show that it was 0. But but here the finite piece can come from anything, so you have to be sure that there is no contribution from here. So, okay, so this is what we derived. In this example, we're no contribution coming from 3 cuts, or contribution we're coming also again from 2 cuts. Okay, and okay, and it's also useful to get finite pieces. Okay, not only the RG running and the anomalous dimension, but also finite pieces coming from heavy particles you integrate out. So let me probably conclude. Okay, so the idea I wanted to show here is that similar you do with fields. And you do effective field theory, that is an expansion of 1 over lambda, lambda being the cutoff of your physics. You can do also have similar approach for amplitudes. Okay, now you have the standard model amplitude 3pt, could define the standard model, the building block of the standard model, amplitudes. But you can add to them other building blocks, amplitudes, that goes like 1 over lambda squared, are easy to see which one you can put in. Okay. And now have at the level, of course, that could be it, but also you can go even at the loop level, okay? And this is the idea was to show you that, of course, there is a derivation of how to calculate the anomalous dimension, but you can relate these loops to, again, on-shell quantities, 3-level quantities. And the important thing I want to show is this emergency, okay? Because now you project into elicities, and there are many zeros in the you can explain there are many zeros already in the amplitude at 3 level, standard model with all particles with minus helicity are 0. These properties at 3 level, okay, built up into zeros at the loop level, okay? So the fact that at 3 level you get many zeros because you cannot have all amplitudes of the standard full being all the amplitudes with all the states in your amplitude being minus helicity, built up when you go to loop level, tells you that also some of the loops are zero. Okay, so this property tree level tells you also zeros at the loop level. Okay, and it can go on in certain examples at even at two loop level. Okay, so zeros here, or if not zero, many contributions are zero. Okay, sometimes the contribution is not zero, but you see that many of them simplifies a lot because still some contribution are zero, so it tells you the contribution can be reduced to couple of diagrams. Okay. So and even when they are not zeros, okay, the other thing I wanted to tell you that they are related, relation that you don't see in the Feynman approach. Okay, so I'll stop here. Okay, thank you.
Thank you very much. Any questions from the audience?
I missed the explanation part of the total angular momentum of the new physics contribution is J equal 1. Because I thought that the electron helicity is flipping, so that I first thought that the 1 over half, minus 1 over half, go to the 1 over half, so that I thought J equal 0, for simply thought. Why is J equal 1 from the new physics contribution?
Somebody can tell me, can you? Can you tell me? Yeah, sorry, because I can hear very badly. I don't know the reason. I don't know if it's because. Are you referring to things, something related with here?
It's a 90-degree rotation. The scatter
Oh my God.
make a 90-degree rotation. The final states, two formulas in the final states. But for G minus 2, you have you make a 90-degree rotation.
Sorry.
I'm Hyun-min. Alex, hi. I don't know if you can see me, but I think just let me rephrase Kimiko's question. Can you hear me?
Hear you very badly. I'm sorry, but I cannot understand it. Don't know what to do.
Can you hear me?
Sorry.
Maybe you don't hear us. Can you hear me?
Yes, but very badly. Yes, tell me.
Okay, I think Kimiko was asking about J equal to 1 amplitude.
So,
Can you repeat?
I can. I asked for the why the new physics contribution part, why J equal 1. So I thought that because the fermion part helicity is flipping, minus 1 over 2 to 1 over 2. So that I simply thought that just becomes 0, J equals 0. So I missed your explanation, I think.
Alex, do
yes.
you hear me? Do you hear
Yes.
me?
Yes, but no.
Did you hear the question?
No. Yes, but I could not understand. Sorry.
You can use this mic.
Maybe you can write on the chatting window. Maybe you can write on the chatting window.
Chat window.
Yeah.
I don't have a clue.
And,
With the microphone, but it's the same.
well,
I can try one more time.
Thank you very much. Can you hear me?
A little bit distorted. Yeah.
Oh. that the new physics part of the total angular momentum J equal to 1.
What is equal to 1? Sorry, what is equal to 1? Sorry.
J equal to 1 from the new physics contribution from higher dimensional operator. Right? J equal to 1 from the after the cutting. For example, a new physics contribution to the angular momentum equal to J equal 1. You said so, right? Maybe the dipole momentum.
So here,
Yeah, right.
This previous right. Not here. Maybe here is okay. Yeah. Here is okay. So I misunderstood. Maybe I misunderstood. But because the helicity is flipping for the dipole moment for electron, so I simply thought that because the helicity is flipping, so that the summation of the helicity is J equals 0. So I think I understood something.
no. There is amplitude. You can see these electrons have to be in a. That's I didn't show why is I didn't show why is J equal 1. Okay. But sorry, here is easy, no, probably, yes. You see here on the other side, okay, this is 0 and this is 1, but yeah, otherwise you have to take, I'm saying not all amplitudes, of course, have J equal, I'm saying this is so simple one, that is this one, sorry. Oops. Okay, I'm saying this so simple one, you can just do the partial wave decomposition and you will see that this is J equal 1, okay? You can see it by the partial wave decomposition, but I think here, looking at here, you can see that this is a state in J equal 1, okay? But I don't know what to say. This is what it is.
Yeah, I think it's because the helicity is flipping from 1/2 to -1/2 in the dipole moment. So
no, because this is sorry, this is minus incoming. Everybody is incoming. Okay. So this is minus a half. You can see this is a -1. Okay. It's already -1. In helicity, -1 cannot be in a spin 0 state. Okay. So this state clearly cannot be spin 0 because this is minus a half is in a state of helicity, total helicity -1. So it has to be spin 1 or higher.
Yeah, right. Sorry, I misunderstood. Thank you very much. Now it's clear.
Thank you. I think what I say here, he can hear well. Do you hear me well? This is not distorted.
More or less.
That's do you hear me now?
Yes.
Yeah, anyway, I ask you. Please go back to the slide for angular momentum selection rule. The amplitude was written with the Wiegand function.
Sorry. Here?
No, amplitude was written by Wiegand function.
To the what? Sorry.
Angular momentum selection rules.
Partial wave decomposition.
Yeah.
Partial wave decompositions.
Here?
Yes. I'm sorry. Yeah. No. Previous slide. Yeah, here. In this formula, the coefficient AJ and NJ doesn't depend on the helicities of the particles.
This, sorry, what depends? The helicity of the particles here is fixed. Yes, this is minus.
No, in the above formula,
What,
in the
what for?
above formula, there are coefficients AJ and NJ.
This?
No,
Here,
no,
this?
yeah, NJ and AJ. As far as I know, in the helicity formalism, the coefficient must depends on the helicities of particles.
The helicities of the part, okay, this is independent of the helicity of the particle. This depends on the helicity of the particles. This this is the Wigner functions. This depends on the helicity of the particles. Yes. Sorry, this is I didn't define. What is H1, H2? Because I didn't want to give detail. I think it's now I think it's I
Yes,
don't know if
this is H1 minus H2, and the light point is H4, H3 minus H4, or the opposite. By the way, as far as I know, the coefficient AJ and NJ must depends on the helicities H1, 2, 3, or 4. So just I wonder about that. You omit the notation in the coefficient NJ or AJ.
sorry, you refer to this?
Yeah, or AJ. 102 has the indexes of helicities of these particles
No, this
in
coefficient.
general.
This depends only on J. This is a normalization coefficient. It's not. It's extracted if you want here. It's not important. It's not important. This is a normalization. These are normalization coefficient of your expansion in partial wave. Okay, this depends only on J. It could be that there are, different expansion, different. Usually, I think this is the usual one, but so helicity can only come because depend on the angle. Okay, so these are the composition of the amplitude in the scattering angle and the azimuthal angle. Okay, and so and the helicity enters here. This function here.
And
I have it here. They give me this, and in this case, give me this because I guess H1 and H2 are the same. So they give me a 0 here.
yeah.
And H4, H4 is 0. And this is minus 1, and I get a 1 here. So the helicity is here, it's 0, 1, these things.
In this case, helicity is fixed, right?
Helicity is fixed, yes.
Then then the coefficient doesn't depend on helicity because we already fixed the helicity. And thank you. And I have a second question.
Minus.
Yeah. I have a second question.
Yeah. This is the decomposition for a fixed helicity. Sorry, I went fast here because this is the ordinary decomposition, partial wave decomposition. I didn't want to emphasize much here, but I didn't define that these are states at definite helicities, and now you can expand in this way.
Yes. And my second question is, please go back to page with the Lagrangian of dipole. F mu, psi bar, sigma mu, F of psi and H. Yeah. You told, I don't know whether I missed your saying, but I remember that you told us that electric dipole term and magnetic dipole term can be written by the Lagrangian term. But as far as I know, the electric dipole term must involve the gamma phi, because the dipole term, electric dipole term is pretty even, pretty old. So
Yeah, sorry, okay. Yeah, okay. Yeah, thanks for the question, because yeah, I was probably here. Yes, you are right. Yeah.
am I correct?
You are correct. You are correct. If I look at this thing in the with a projection in general, okay, if this is the same field, yeah, you are right that this is a the dipole is like this and the other is a gamma 5. Yeah, sorry, because the notation was what I meant here is this type of operator. This type of operator, okay, without specifying the details, okay, because in the standard model, this operator, yeah, is this one. I'll go back to tell you exactly what is the operator. There is, in the standard model, you decompose, you separate left and right fields, okay?
Yeah.
And in this case, it's different, okay? So what you say is correct when you go to the psi bar is the same field.
Yeah.
But in the standard model, of course, we talk always about, because the transformation rules under the gauge symmetries of the left and the right are different. You split the fields in left and right. So sorry, where are the dipoles? So okay, dipoles and down here. Okay. So okay, this is for the U1. Okay, so
Yeah.
okay, the leptons are here. Sorry, so here we have the left. This is the left, and this is the right. Okay, so now when we split in left and right, okay, now okay, you can, there is only this operator. Okay,
Yeah.
the gamma phi in the middle doesn't do anything extra. Okay, there's only this operator, and now in this definition where you have left and right here, the dipole, what I was saying is that the coefficient here, there's a coefficient here, okay, and if it's real, the real part goes to the magnetic, okay, and the imaginary part goes to the electric dipole moment, okay. That is equivalent what you said. It's completely equivalent, okay. So when I write this thing as in Dirac notation, psi is the same, okay. If this, you see here are different fields. This is the left and this is the right. That in the standard model, two different guys kept transforming. Okay. If I go to the Dirac notation, I put the psi, and I write psi left plus psi right. And now you are right that I have this sigma mu nu psi, and the psi bar gamma 5 sigma mu nu psi. Yeah. So I have this. This is the dipole, magnetic dipole, and this is the electric dipole. You are right. Yes. Okay.
Yes. Thank you so much.
Okay.
Any other questions? Let me ask one question. Here you assume the massless state for weak gauge bosons and standard model fermions. And what aspect is maintained and what aspect will be changed when you consider the massive fermions and massive weak gauge bosons?
When one goes from massless to massive, this is your question, going from massless to massive?
Yes, that's right.
Yeah. When calculating the loops, the anomalous dimensions, nothing changed, okay? Because the anomalous dimension, you can calculate them in it has to do, the anomalous dimensions has to do with the UV divergent part, okay? So in the UV means a high energy, the masses are irrelevant. Okay, so even if I think that in the standard model, the fermions and the gauge boson get mass, some of the gauge boson gets a mass, for calculating the anomalous dimensions, because this is depending on the UV part, doesn't change anything. The anomalous dimension is the same. This is why we can calculate them in the massless limit. Okay. Nevertheless, it is true that they're going to calculate amplitudes. For example, the amplitude I was showing before will change, because if the fields have masses, will change. In particular, okay, I was showing you this calculation. Okay, it was the amplitude I was calculating will not be okay. This calculation will change. Okay. So to this calculation, if this state W is massive and these fermions are massive, this is not going to be any more true. Now there is still a formalism. I don't know if somebody, I don't know if Yutin, Juan or Cliff told you that there is the spinor helicity formalism can also be implemented for massive states, but involved is a little bit more complicated, because as we were saying here, the helicity formalism is simple because it involves, whoops, what it is. It involves for each particle involve only one spinor or anti-spinor. If it's this p square, okay, this is only true. This is true, okay, true for p square 0. Okay, so if p square is different than 0, you need two spinors. Okay, so you will need a spinor p and another spinor called p prime. Okay, we will need two type of spinors. Okay, to have to relate. Okay, in some sense, let me write it here. So what I'm trying to say is that you cannot use this formalism for mass for this formalism is only useful for p square 0. So you have to change the formalism, and you have to include and one way it was done, is already a lot of people going through this, calculating amplitudes also for massive, is that you need to incorporate in this here another spinor. Okay, so each particle will be, massive particle is defined with two spinors instead of one. Okay, here we were talking about one particle is defined but with one either a spinor or anti-spinor. Okay, either the angular spinor or square spinor. So you will need to double this. It's a little bit more complicated, but it still is kind of useful. Okay, so when you go to massive, I'm trying to answer this. When you go to massive states, the spinor, you lose a little bit of the simplicity and the power of the spinor helicity formalism. You lose a little bit of it, but not completely. Still, there is some power there to calculate amplitudes in a relatively simple way. Okay.
Good. Thank you. Any other questions? If not, let's thank Alex again. Thank you very much. Have a nice day.